Hello. In Unit 2, the focus was on protons and neutrons, the particles that contribute the most to the mass of an atom. Protons and neutrons also determine the type of element and isotope an atom is. In Unit 3, though, our attention will turn to electrons and the electronic structure of the atom. And these are two cartoons of different models of atoms. But to understand the nature of electrons, we should first discuss different types of energies and how charges interact with one another. These are the details if you want to put a title to your notes. Again, in this video, we're going to specifically look at kinetic energy and potential energy and how they relate in the context of chemistry. Okay, the first thing is some definitions. First definition will be kinetic energy. And that's energy that results from motion. Let me give you an equation, and I like to put my equations in green so I can easily find them in my notes. And the equation will be Ke equals 1/2 mv squared. Let me put a box around all of our key equations. When you learn equations, what's important is that you also understand what units to use, because if your units are incorrect, then you're not going to get the correct numerical answer. And for kinetic energy, actually we'll save that for last. M is mass, but the mass here has to be in kilograms for the equation to work. V is for velocity, and the velocity is going to be squared. So what can we do? We could say this is velocity. Velocity is meters per second if you're using SI units, but the whole thing is going to be squared. What does that mean? If you do the math and the analysis, the unit analysis, kinetic energy will have a unit of kg dot meter squared, because that velocity was squared, over second squared. But this is also can be simplified into an energy unit called the joule. So all of that equals joules, and a joule is the SI unit for energy. You may not be familiar with joule to measure energy, but maybe you are familiar with calorie. Okay. So there is a conversion to go from joules to calories and vice versa. And calorie is also a unit for energy, or a unit of energy. But we'll use most likely the SI unit, the standard unit, or the International System unit for energy. All right. One last thing about the joule. 1 joule, 1 J equals. If you think about it, we have 1 joule on the left. What's the combination of mass and velocity that could give me 1 on the left? 1 joule comes from the energy of a 2 kilogram mass traveling how fast? Okay, because we want all of this to equal 1. So 1/2 times 2, okay, equals 1 times maybe 1 squared. So traveling 1 meter per second. If you plug in those numbers, you'll get 1 for the kinetic energy, 1 joule. Okay, next thing. Kinetic energy can also be related to temperature. Our next equation, which we're not going to use a lot in this unit, is kinetic energy average, the average kinetic energy, equals 3/2 RT. Again, in green, but also I like to box my equations. This R is a gas constant. We're not going to talk, again, a lot about this equation. This will come up when we actually talk about gases and how the movement of gases can be related to the kinetic energy and temperature. The temperature here is going to be in degrees. It's called Kelvin. Again, both of these concepts discussed later in future unit videos. Okay, that's all I want to say about kinetic energy. We have to move on to potential energy. Let me just find my notes. Okay, potential energy is next. Potential energy is energy of an object due to its position. I know it's kind of an abstract definition. I'll explain a little bit more. But from physics, you know that if you have a ball up on top of a hill, that it has a lot of potential energy. It has the potential to create energy, in this case, kinetic energy. In physics, let's have a hill. Let's have a ball. And that ball is, even if it's still, it still has potential energy. It has the chance, right, of rolling down the hill, convert potential energy into kinetic energy. That's what they mean by position. But this could also relate to chemistry. And in chemistry, there are two ways to think about, or two manifestations of potential energy. The first one is chemical potential energy, or just plain chemical energy. Actually, output potential also. And that's potential energy stored in substances. We'll say PE. That's also a little bit abstract. Let me give you an example, i.e., energy released when forming or breaking chemical bonds. We're not going to talk much about that because we haven't really yet talked about molecules and how they form from atoms and how reactions can take place to break or form chemical bonds. What we will talk about in this video is a different type of potential energy, which is electrostatic potential energy. And I'll have time. I want to do at least one problem in this video, and it will be based on electrostatic potential energy. That is from the interactions of charged particles. And we know that from our previous unit that the nucleus is positively charged, and here in this unit we'll look at electrons which are negatively charged. This is potential energy from the interaction of charged particles. Now these particles can be a single electron, a single proton, or they could be a nucleus which has many protons, or an atom that has many electrons. Okay. It doesn't just have to be a single particle. Now this is still energy that comes from or due to its position, because the farther charges are, that affects the potential energy. Okay. As you bring charges closer together, again, that will affect the potential energy. And the way that is affected is via this equation. E, and I'll put EL for electrostatic, equals C Q1 times Q2. Those will represent the two charges, or the two charged particles, and D, distance. Okay. We call this the electrostatic potential energy equation. It's not quite Coulomb's law. It's very similar to Coulomb's law, but remember Coulomb's law talks about force and the distance is squared. Okay. Very similar, but not quite Coulomb's. This is electrostatic potential energy equation. Same thing as we've done before. Box your equations, and again, the units are going to be super important. For instance, for this one, if we thought this was grams, then our calculation for kinetic energy will be 1,000, a factor of 1,000 off. Okay. I forgot to give you one thing about this equation. There are some textbooks that change the symbols a little bit. Some textbooks I've seen use energy kinetic like that, equals 1/2 m, and then instead of a v, they use the Greek letter mu. So that's a u. Okay. I'm not going to put the tail that's usually with there. We'll just call it regular u, actually. 2 squared. Okay. You may see that in the book. That represents this equation here. 1/2 mv squared. Good. Got that out of the way. How about some units on this electrostatic potential energy equation? C is a constant, and it's a positive constant. D is distance between the two particles. Okay. Q's. These are the two charges. And you're going to see a sign, plus or minus, and most likely an integer. Okay. -1, +2, +4, etc. Now, I'm not giving you units, okay? Because for the most part, at least in my class, I'm not going to ask you to calculate a number. Let me write that down as a reminder to myself. Calculate the number or the absolute energy. Instead, we're using this equation to compare two different systems, to say, oh, this system has maybe twice as much energy, or half as much energy as another system with different charges and different distances. So instead of asking you or my class to calculate the absolute energy, we'll use this equation to compare two situations. So it's a relative energy to systems. So this is called relative. And therefore we don't need to have units. Okay? We could say one system has 5 times as much energy and the 5 times as much potential energy as another system. Let me give you an example. Hopefully this will solidify. The question in this example is how much greater, okay, we're doing a comparison, is the electrostatic energy or electrostatic potential energy of a system that has +2 and -2. Those are your two charges. Let's see, how much greater is the electrostatic potential energy of a system that has +2 and -2 particles versus a system that has +1 and -1, and we'll say both systems have the same D. This is going to be a little bit tricky, but when you think about comparison, for instance, if I drive to school at 60 miles per hour and my friend drives to school at 40 miles per hour, you know, how much faster am I going? You would take 60 divided by 40. Okay, let me take my calculator. 60 divided by 40, 1.5. Okay, see how if we take a ratio 60 to 40 and we reduce it to 1.5, I can say that I'm driving 1.5 times faster than my friend. We're going to do the same thing here. We're going to try to figure out how to get a ratio between the two systems and ask ourselves how much more energy is the system with more energy over the system with less energy. Now there are a couple of phrases that I think you remember or that you are familiar with. That's opposites attract. We'll start with that first. Opposites attract. What that ends up being in this equation, when you have a plus times a minus, is that the whole energy will be negative. And that means that there's an attractive force. So E, besides knowing the units for an equation, it's also good to understand the magnitude of the type of answers you'll calculate, but also the sign, right? Signs are going to be very important because in this case, electrostatic potential energy is negative. And what does that mean in layman's term? Negative electrostatic potential energy means that it's an attractive force. In contrast, you have like charges repel. Repel or repulse. And in that case, electrostatic potential energy is positive, and that's a repulsion. Okay. We expect for both of these systems to be negative, okay, but we can still compare both of these to each other. And the way we do that is we take a look at our equation, and we are going to isolate the variables and the constant. Okay. And then we're going to relate the two systems to each other. So let me work through this step by step. The first thing is we'll call this situation A and this situation B. Okay, system A and system B. For system A, we'll just put in the equation what we know. Okay, system A has +2 and -2, the Q1 and Q2. +2 times -2 over D. Now, yeah, we could put numbers to these. The question could have, or the problem could have given you numbers, but it's just as good as them giving us variables. We want to get this to a situation where we have variables on one side and constants on the other. This d is a constant because it's the same d in both systems. The c is a constant. But the energy is going to be different and the charges are different. Okay? What I'm going to do is I am going to divide. What am I going to do? I'm going to take this. Oh, that's what I'm going to do. I'm going to take, I'm going to bring over this term, the -4, to the other side. Let's see if this works. EA over, now we have -4. Okay. Right. Divide both sides by -4. And on the other side, we have the constant, and we have the distance. Again, the idea here is to have variables on this side and the constants on this side. You'll see why I want to do that in just a bit. Because I'm going to do the same thing for the other system. Now, it's going to have a different energy. Well, it actually may have the same energy, but right now we don't know that. So we'll call it electrostatic potential energy for B equals C plus 1 minus 1 over D. And check my math. Bring that over. It's -1, right? And equals CD. Now, do you see how both of them can equal C over D? And these are constants. So I could set these two equal to each other. This should be B, right? This should be B, sorry. Oh my goodness. Okay. Alright, so these two can be equal to each other. E A minus 4 equals E B minus 1. And both of them have a negative. We could get rid of that. Okay. And what are we looking for? We're looking for how much greater EA is over EB. Because take a look at these two systems. We should have actually estimated this first. Which one would have the bigger electrostatic potential energy? Well, with D being equal and the C being a constant, the bigger this number is, Q1 times Q2, the bigger that the electrostatic energy will be. So this would have a greater potential energy. So what I really want is that ratio. I want the EA over EB. Just like with that driving analogy, I'm driving 1.5 times faster than my friend because I put the bigger number on top, the 60 miles per hour divided by the 40 miles per hour. What do I get if I try to do that? I have EA on top on the left. If I divide by EB, okay, then what do I do with this 4? This 4, I have to multiply both sides by 4. So this will be 4 over 1. There's the ratio. Just like I drive 1.5 times faster than my friend, the electrostatic potential energy for EA is 4 times greater than that for EB. And that was predicted that EA would be bigger. 4 times greater. Now, could you have done this in your head? Sure, you could have done this in your head, but what if the charges weren't as easy? What if it was +1 and -3? What if in one system the distance is D, but in the other system the distance is 3D, 3 times as far, or far from each other? Then it gets a little bit hairy, but if you follow this strategy of separating variables and constants and then setting the two systems equal to each other, eventually, if you know what ratio you're aiming for, okay, then you could have that ratio here expressed, and you'll have a multiple, right? 4 times greater, or whatever times greater one over the other is. EA is 4 times greater than EB. Okay, so I know that both charges were decreased or lessened. Okay, it went from +2 to +1 and -2 to -1. It went down one numerical unit, but that resulted in an energy that is 4 times greater. Okay, that is basically all I want to say about energy. It's really just an introduction. Again, in future units, we're going to look a little bit closer into some of these other energies like chemical, especially chemical potential energy. Last thing, I would be remiss if I didn't at least put down the law of conservation of energy. And what that means is that energy cannot neither be created nor destroyed. Also, it means that PE can be changed into KE and vice versa. They're interchangeable. And the PE, again, can be chemical or electrostatic. Okay, spelling is not great. The kinetic energy could be motion or heat, temperature. Okay. And last thing is total amount of energy in the universe it's called conserved, neither created nor destroyed. Okay. The next couple of videos in this unit, we will look at light, electrons, the energy of light. Okay. That's why it was essential that we have a good understanding of energy.